I got a couple of questions which I want to address. These were about 21B post-class assignment, the problem number 3, the post-class assignment 22B, the problem number 2, and finally the post-class assignment 22E, the problem number 1. Okay, let's start from the 21B number 3. So what we are given is the following combination of two batteries. So this is battery number 1, this is battery number 2. The EMFs of both batteries were given. I do not specify these numbers. I will save. I will solve this problem in the most general terms. Then also the internal resistances for both batteries were given. Okay, what we need to find is the actual current through this circuit, not only its magnitude but also the direction. And this is what we are going to do. Additionally, what we need to find is the terminal voltage. The terminal voltage is the potential difference between these points. Okay, it's the potential difference between the points of the connected battery over here, where so it's essentially the voltmeter will be placed over here. Yeah, so the voltmeter will be placed over here. And this is what we need to measure here. It includes also the fact that there is internal resistance in this battery, right? So it's not just the EMF of the battery. It also includes the fact that actually these batteries are connected, and to find the terminal voltage, we need actually to find the current as well, right? So, and this is what we are going to do here as well. So here I define the direction of the current quite arbitrary. Okay, so I just picked the clockwise direction. If I get a negative sign for the current eventually after I would substitute the numbers, then it would mean that the current flows in actual different direction, right? Okay, so in principle, one can solve this problem by just finding the equivalent EMF and equivalent resistance. But why don't we just apply the Kirchhoff's rules, which we already know, and therefore we can simply solve this problem by applying Kirchhoff's rules. To apply Kirchhoff's rules, I need to define the potential difference direction for all the EMFs, and here I did it for EMF number 1, so it's from negative terminal to the positive terminal, always for the battery. The same is for the EMF number 2, right? So it's from negative to the positive terminal. Then since I define the direction of the current in clockwise direction, then the potential difference across the resistor R1, well, it's opposite to the direction of the current, right? So and it will be like this. Now we go around this loop and we see the contribution of the internal resistance of the battery number 2, and again, so the current goes in this direction, right? Then the potential difference is directed across this resistor is opposite to the direction of the current. Very good. So now I would like to write the loop rule, okay, the loop number A, the loop A. So the loop rule for this loop, here we go. I will start from the EMF number 1. E1 contributes with a positive sign because the direction of the loop coincides with the direction of the potential difference, E epsilon 1. Now I go around this loop and I see the EMF number 2, and its direction is opposite to the direction of how I go around this loop, and therefore it contributes to this equation with a negative sign. The next part is the potential difference across this resistor. It's opposite to the direction of how I go through the loop, so it's big, and this is why there is a negative sign. And finally, the last resistor, and the same rule applies to it as to the resistor number 2. The direction, we have a negative sign, right, because of this this direction of the potential difference, and direction of the loop is opposite to it, negative sign. Fine, so what I need to do, so essentially epsilon 1, epsilon 2, R1, R2, these are all given in this problem. What we need to find is the current. Okay, we can just transfer these terms to the right-hand side, and then I will rewrite this equation starting from the right-hand side, and the left-hand side will appear on the right-hand side now. Very good, now I can simplify and I find the common terms, so the common factor, it's I, the current, and then I can divide both sides by R2 plus R1, and I will get the final result for the current. Okay, And this will define not only the magnitude but the direction, because I will know the sign of this expression. So for example, if epsilon is greater than epsilon 1 is greater than epsilon 2, then the current will flow clockwise. Is epsilon 1 is less than epsilon 2, then the current will flow counterclockwise, right? Because the sign will be negative in this expression. And if epsilon 1 equals to epsilon 2, then there will be no current, because this will just cancel each other. Okay, so I solved this problem in full generality, yeah, for the current. So now let's look at the potential difference, the terminal potential here, terminal voltage over here. For this, I need to find the potential difference between the point B and A, between the point B and A, or A and B, right? So it's VB minus VA. Very nice. So I can just look at this part. So epsilon 1 will contribute with a positive sign, right? Positive sign. And so this is my potential difference I want to find. Epsilon 1 will contribute with a positive sign. And this contribution, I times R1, will contribute with a negative sign. Then I can just substitute the current which I just found, okay, and obtain the following expression: and epsilon 1 times R2 plus epsilon 2 times R1 divided by the sum of the resistances. Okay, very good. So essentially the problem is already solved, because the potential difference between these 2 points is the same as the potential difference between these 2 points. So we found the potential, the terminal voltage already for both batteries. But if you really want to cross-check that indeed the mathematics brings you this way, let's just look at this delta V1. For delta V1, I write the same. It's epsilon 2, so I'm finding the potential difference across these 2 points. Yeah, so it's epsilon 2 with positive sign. Now, this contribution over here, yeah, so I can write this in the following way. This is either plus R2 times this current, yeah, either plus I2 times this current, okay, or I can just write this in the same way as you would usually do that. It's just R2 times the times the negative current over here, right? Because the current, when you consider the potential difference over here, usually would be in the opposite direction, right? So the current usually is, when you consider just one battery, the current, you would usually prescribe it to face this way. That means that the current goes from the positive terminal, yeah. So and in this case, this potential difference across the resistor R2 will be in the opposite direction. But in either way, you will get the final result, which will reproduce that. Okay, if you change the sign for the current, decided over here, or if you just compute it without doing this, you just won't compute the potential difference from this point to this point. Yeah, let's just do this. So what you're going to write that it is given by epsilon 2, yes, plus I R2. So why plus? Because again, so I'm looking for the potential difference between these 2 points, yeah, and then this potential difference across the R2 is directed in the same direction, epsilon 2 directed in the same direction, and the current is whatever it is, right? So the current we already found. So let's just substitute this number, the current into this equation. What I get is epsilon 2 plus, what's the value of the current? It's over here. It's epsilon 1 minus epsilon 2 divided by R1 plus R2 times R2. Okay, and one can simplify this. And you will be able to see that you will get the same result. So it is epsilon 1 times R2 plus epsilon 2 times R1 divided by R2 plus R1. Okay, and this is the solution of this problem. Okay, so now let's look at 22b. At 22b, I'm not going to solve this, but I want to just kind of guide you through that logic of this problem. For 22b, you need to remember. Okay, so this is the Earth. Okay, so my poor picture of that Earth. So this is the Earth. So this is geographic North Pole. Okay, geographic North Pole coincides with the South magnetic pole. That you have to remember. The geographic North Pole coincides with the South magnetic pole. And therefore, if I would like to write, to show the magnetic field lines, they will look like this, right? So, well, and there is, of course, will be the ones which will be symmetric here as well. But essentially, they originate from the south geographic pole, and they go into the north geographic pole. Very good. So it means that here, in the northern hemisphere, they approach somewhat, from above, right? So they form like they try kind of point more down towards the Earth, and vice versa in the south hemisphere, the magnetic field points somewhat up, right? So as shown in this figure, Okay. And that's essentially all you need to know to solve this problem number 2. Okay. We did something similar in class as well. Fine. So, and then the last problem is 22e. That's the problem number 1. And in the problem number 1, this circuit was given. There was a switch, which they say that the switch was closed for a very, very long time. Okay, yeah, okay. So the switch was closed, and therefore I just replaced it with a piece of the wire. It was closed for a very, very long time. It means that the condensator, capacitor over here, was fully charged. If the capacitor is fully charged, there is no current through this capacitor. If there is no current through this capacitor, this all here is just like some redundant piece of the wire. So let's get rid of this redundant piece of the wire. There is no current through this wire, right? So we get rid of this piece of this wire, and therefore we can redraw this circuit only by taking into account the elements over here. This is not relevant at all. So, and this is what I've done over here. Just redrew this circuit with just the elements through which the current actually would flow. Okay. So, and here I have 2 resistors. So let me just replace them with the equivalent resistor with the resistance of 3 ohms. So 2 plus 1 is 3. For this specific problem, there was these numbers, but you might have some different numbers in your homework, but it doesn't matter. So next, what I have the 6-volt battery EMF, okay, here. And what I need to find is the current. Well, when I know I will use the Ohm's law, and the Ohm's law tells me that the current is given by the EMF divided by the resistance. So resistance is 3, the EMF is 6, so I get 2 amperes. Okay, it will be different if you would be asked to find the current, say, through the battery at just right after you close that switch. Just right after you close that switch, it will be different. The solution will be different, right? Then, because here there will be a current through the capacitor. Okay. Think about this, how to solve this problem. Then, I'm sure both of the examples like this, or both of the problems like this, will be on your test.